So welcome back, everyone. So this is going to be lecture 2 of convex optimization, and we're going to do convex optimization for reals this time. So we're done with the motivation. So lecture 2 is going to be about a single algorithm, the most simple one, gradient descent. Okay, so what is gradient descent? What is this algorithm? It goes like this. So at first I'm going to talk about the unconstrained case. Okay, so we're just trying to minimize a convex function with no constraint over all of Rn. So the algorithm looks like this. It's an iterative method where the t plus 1 step, xt plus 1, this is the following equation. It's equal to xt minus a step size eta times the gradient of f at xt. Okay, so we're trying to minimize this convex function f, and what we're doing is currently we're sitting at some point xt, we calculate the gradient, and we move in the negative direction of the gradient. Okay, we do a little step in that negative direction, and that's our new iterate. And we keep going like that, okay, and hopefully we want to reach the minimum of the convex function. It makes sense? That's like the simplest possible algorithm. So this goes back to the mid-1800s. I think Cauchy was the first one to use it, so he just had some, optimization problem in a 6-dimensional space. So he was trying to identify the position and the velocity of some planet, and he had a lot of data. He was trying to do some kind of least squares. And those 6-dimensional problems, this is high dimension when you're doing it on paper, right? I mean, on a computer, it's not really high dimension, but when you're trying to optimize on paper, it's really high dimensional. So you want some simple rules that you can, iterate by hand. So this is what he was doing to find the solution. Yes?
Newton's method.
Right. So Newton's method is different because you have an inverse Hessian, and that's exactly the problem. Is that for a 6-dimensional problem, you have this 6x6 matrix that you have to invert, and that's painful. So what Cauchy was exactly trying to do was to go at a simpler method than Newton's method. Yeah, but good point. Any other question? Okay, so what's the intuition of this? I mean, I know you all know the intuition, but let me write it. Why is this a good idea? So the intuition goes like this. Locally, when I do a first-order Taylor approximation, my function f at some point y, this is roughly f of x plus grad f of x in a product with y minus x. Right? This is Taylor's theorem. So there is a remainder term which is of order of the square of this. Okay, so when I'm at small distance, when y is close to x, this is true up to a term which is the square of this small distance. So now what does that mean? Picture, like in a picture, you have this point x, okay? And really, this is a gradient direction. Okay, so this is a grad f direction, grad f of x direction. And what do we know? We know that orthogonal to this direction, the function is basically not varying. I mean, it is varying, but it's varying more like a square. Okay, so it's going very slowly. It's going like t squared when I go away from this point on this line. Whereas on this direction, it goes like a linear function. Okay, and it goes like a linear function, and if this is a negative gradient, if this is minus grad f of x, when I move in this direction, I go down on the function. And when I move out in this direction, I go up on the function. Okay, and if I move orthogonal, I basically don't move. So if I want to spend my energy, if I have a unit norm energy to spend, the best way to spend it is to move in that direction. Okay, so this is the intuition of gradient descent. All right, so now let's see what, so this is a general intuition that goes beyond convex optimization. So now let's see what happens when you have convexity. Okay, so with convexity, what do we have? Well, we know the following. With convexity, we know, remember the convexity definition is that f of x minus f of y is smaller than grad f of x in a product with x minus y. Okay, this is just the property that the function is always above its tangent. All right? So if we look at this inequality with y equals x star, so with y equals x star, what do we get? We get the following. So let me introduce a notation, delta of x. This is a suboptimality gap, which I define as f of x minus f of x star, we get that this suboptimality gap is smaller than grad f of x inner product with x minus x star, which I will rewrite with two negative signs as minus grad f of x inner product with x star minus x. Why did I do that? Because here you see this is the correlation. You're sitting at x, and you want to get to x star. So the direction in which you want to go is x star minus x. That's really what you would like to add to your point. But instead, you add minus grad f of x. And what convexity is telling you is that what you're adding is indeed positively correlated with the direction in which you want to go. And how much positively correlated? Exactly positively correlated by the suboptimality gap. Okay, so again, the picture now, let me just redo this picture. We're here at x. This is minus grad f of x. And what this inequality is telling us is that x star, first of all, it's telling us that x star is in this half space. Okay, so I'm making a move in the correct direction. I'm going towards x star. X star cannot be there. Okay, so that's convexity. And moreover, I know the following. So if this is, this is the true direction that I would like to follow, but instead I followed that. And what is this inequality telling us? This inequality is telling us that this projection, okay, so the progress that I make on the direction to x star is exactly lower bounded by the suboptimality gap. This progress, so this is the progress on the x star minus x direction is lower bounded by delta of x. Okay, and now I'm going to show to you in just a couple of lines that this line immediately gives you a rate of convergence. Tells you how fast you're going to converge to the optimum. Kind of makes sense because you're saying, you're relating your distance to up to your suboptimality gap. So you can say, if this was big, then I'm making a lot of progress. Okay, so the only way for me to slow down is actually if I'm getting pretty good. Any question on this intuition?
What is this delta?
Yeah, sorry. So delta, I define it here. Delta of x, yeah.
I thought that was an F.
Yeah. Sorry about that. That's my bad. Yeah. All right. So let's do the analysis. So another way to write this progress on the x star minus x direction is lower bounded by delta of x is like this. This is the same thing as saying the rate of decrease of distance to opt. Okay, so sometimes I will call x star opt, and what I'm saying here is the rate of decrease of distance to opt is lower bounded by suboptimality gap. So let's do, okay, so all of these were English words, so I'm trying my best to not write down an equation immediately, but there is a very simple equation that witnesses this sentence, and it goes like this. So let's do a continuous time analysis. Okay, so the continuous time analysis is going to be like this. Instead of having this discrete process, note that there is a little thing which is a bit annoying. Here I made progress on this, but I also got away from this line, because I didn't move exactly to that point. I moved a little bit up from that. Okay, so you need to take care of that. I don't want to do that for now. So the way I'm not going to do that is that I'm really going to look at things in continuous time. So let me define a process, a continuous time process, by the following equation: d over dt of x of t. Okay, so now x is a continuous time process. This is equal to minus grad f of x at grad f of xt. Okay, so this is called the gradient flow. Okay, it's continuous time gradient descent. This is not per se an algorithm that you can implement in your computer. What you can implement is gradient descent over there. Okay, but presumably if eta, the step size, is small enough, this should be a pretty faithful representation of what gradient descent is doing. Okay, and the analysis will be simpler with that, and then I will do the discrete time analysis. Okay, so let's look at the measure of progress that we care about, which is the distance to opt. So x of t minus x star. Okay, so we want to take the time derivative of this thing. That's what we care about. But if you have some experience with taking time derivatives of, derivatives of norms, you know that it's nicer to take the derivative of a norm squared. Okay, because a norm squared is, you write it as an inner product, there is no normalization, so this is simpler to differentiate. 1/2. Okay, so what is this? Well, I just differentiate this norm squared, so I get a 2 that gets out, and then I get the inner product between what's inside and its time derivative. Okay, so this is equal to the inner product between xt minus x star. Maybe, let me write it like this. It's the inner product between d over dt of xt minus x star and xt minus x star. Right, this is just the standard inner product in Rn. So what is d over dt of x of t minus x star? Well, by definition, it's minus grad f of xt. X star is not moving. Okay? So this is equal to minus grad f of x of t inner product with x of t minus x star. Sorry, I use 2 different notations for the inner product, but there is no reason for it. Okay, it's just, that's how it is. Good. Now, by convexity, I know that this is smaller than minus delta of x of t by convexity. Okay, so in continuous time, I exactly get an equation that is literally that sentence. The rate of decrease of my distance to opt, where the distance is Euclidean norm squared, is exactly lower bounded by the suboptimality gap.
Should it be greater than or equal to?
Let me see. So I want to say this without the minus is bigger than f of xt minus f of x star. Yeah. Which is good because that's the direction we want to say. We want to say this is decreasing fast. Yeah. So you know the rate of decrease is minus that. Okay, anyway, you get it. Okay, so now let me just integrate this inequality. Okay, so integrate over time. What do I get? I get that the integral, okay, let me just be slow. And okay, the integral of d over dt from time 0 to time tau of 1/2 the norm of x of t minus x star squared dt. This is lower bounded than minus the integral from 0 to tau of delta of x of t dt. Okay, and I know exactly what is this integral. This integral is exactly 1/2 of the norm of x at time tau minus x star squared minus 1/2 of the norm at time 0. Okay, and let me denote this by r0 squared. Okay, my distance to opt at the beginning is r0 squared, just some number. Okay, so what do I get? Let me rearrange. I put that on the left side, and this thing I just lower bounded by 0. So what I get is the integral from 0 to tau of delta of x of t dt is upper bounded by r0 squared over 2. And let me normalize so that I have averages, because with convexity we like to take averages. So let me normalize by 1 over tau. 1 over tau and 2 over tau. Okay, so I see that the average suboptimality gap that I observe on the trajectory of gradient descent is bounded by this term, which is going to 0 as tau goes to infinity. Now, if I want to, so that's a good result already. We see that if I take a random time on my trajectory, I get a pretty good point. But by convexity, I can also give you one point, which is good, which is the average of those points. Okay, by convexity, notice that the delta function is also convex, right? I mean, f of f is convex, so delta is convex. Okay, so I know that also implies that in fact delta of 1 over tau integral from 0 to tau of x of t dt, this is also upper bounded by r0 squared over 2 tau. But remember, the definition of convexity is that when I take averages, I get a better point. Okay, this is the definition of convexity. So when I take this average, I get a better point than if I average the point. And when I average the point, I get this value. Yes?
What was R0?
Yeah, R0 is just the distance to opt at the beginning, at time 0. R0 is just the norm of x0 minus x star. It's how far you started from opt. Okay, so this is a result. Okay, a good result. This is saying that I run gradient flow. Okay, I run gradient flow for up until time tau. And if I take the average over my trajectory, I get a point which is good. How good? It's good up to r0 squared over 2 tau. So now let's see what does it tell us for the discrete time. Because again, this is not an algorithm that you can code and implement per se. Okay, you have to discretize it. All right, so let's do the intuition for the discretization here, and then I do the formal proof. Okay, so now discretization. So run gradient descent with step size eta, okay, which I also call learning rate sometimes. So the step size eta for capital T steps. Okay, so what do we expect? If you run it, with step size eta, what is gradient flow doing? Gradient flow is running gradient descent with step size dt. Okay, so here I'm running it with step size eta. So if I do that for t steps, I expect to be at time on the gradient flow, tau, which is t times eta. So I expect to be at tau, which is t times eta on the gradient flow. Okay, so my expectation is that when I run gradient descent for capital T discrete step with step size eta, I'm basically at the point on the gradient flow at continuous time tau, which is t times eta. So of course, if I stop the analysis here, I'm like, okay, so then I get a convergence rate, which is 1 over capital T times eta. So why don't I take eta to be very large? Right? This doesn't make sense. Of course, here what I didn't take into account is that there is some errors that I make when I do this discrete time, discretized version. So what is the error? Maybe I was a bit optimistic that this is enough space. Let's see. So what is the error that I make when I do this eta step? Well, let's just look at it on an example. Say that I'm optimizing this function, just the absolute value. Okay? This is the function that I'm optimizing. This is an honest convex function. There is not hiding anything. So what's the problem? The problem is I could be here, very close to the optimum, but my gradient is telling me, -1, like move step 1 in that direction. So if I do that with a step size eta, then I will end up at some point here, which is at distance eta. Right? So the error that I make is of order eta. Right? So what I will get in my convergence rate is that I will get this discrete time, discretized gradient flow, plus an eta mistake. So let's be a bit more correct. So here you see now what is important is actually to know the norm of the gradients. If the gradient can be very, very steep, then I can make a bigger error. Notice that this analysis so far used nothing else than convexity, pure convexity, nothing else. But right now we see that we need an added assumption, which is that the function is Lipschitz, that the norm of the gradient is bounded. So if the norm of the gradient is bounded by L at any x, what do I get? Then, at most, I overstep eta L. Okay, that's the distance that I overstep, eta times L. And what is the error? So the error, if I might distance eta L from the optimum and my function is L Lipschitz, then my error is eta L times L. So the error is eta L squared. Okay, so let me write this, and then we're going to take more space. Sorry about that. I'm kind of stuck in my little corner right now. So what do we get? We get R0 squared, let's forget about the 2, over capital T eta, plus eta L squared. Right, so that, yes, please.
Y squared?
Say again?
Can you repeat again why it's the square?
Yes. So this is a distance, right? Eta times L is how much I overstep in terms of distance. But my function is L Lipschitz. So in terms of value, I'm L times this distance away from opt in terms of value. Yeah, actually, another way to check all of these things is that this is a number, this is like a value, a function value. So it should have the units of my function value. So you can check, just make a unit analysis of this equation, and you will see that you need an L squared. That's a bad way to do it, but anyway, yeah?
So you talked, I'm not clear what the error is. Is it the error of this integral?
Good. Yeah. So it's okay to not be completely clear, by the way, because I'm going to make it formal in a minute. This is just the intuition. The error that I'm saying is compare this value with 1 over t, the sum for t equals 1 to capital T of f of xt. Okay, minus f of x down. Okay, so I'm comparing this with that. Okay. So I get those two terms. So when I optimize, you see I have a 1 over eta plus eta. So when I optimize, I get the geometric mean of those two things, right? The square root of the product. So this is going to be bounded by R0L over square root T for good eta. For eta, which is, let's just write it, eta is R0 over L square root T. Okay, so if you go for capital T times step, you take this step size, which is R0 over capital L square root T, and what we expect from this analysis is we will have a convergence rate of R0 times L over square root T. Okay, so a 1 over square root T convergence rate. Let me give one more sentence about the interpretation of those quantities. This, you can really think about it as the rate at which you forget your initial condition. This is where the R0 comes in. Okay, you started far away, and it's going to take some time, even if you did the gradient flow, to forget that you started from a bad point. This is forgetting of initial conditions. What is this term? This term is exactly the error from your discretization, which you can think about as a kind of a variance term. You're not exactly on the gradient flow, you're kind of jittering a little bit around the gradient flow. So this is a variance term. Okay, so you have a range or like distance to opt at the beginning and a variance term, and when you optimize the two, you get this 1 over square root T. Okay, so now I'm going to just prove formally this inequality by doing directly a discrete time analysis on, these iterates over there. Are we clear on what we're doing and where we are?
So this is going back a little bit, but in my intuition says the longer you run this continuous time algorithm, the better your
point is.
yeah. So why are we taking this average of our trajectory?
Very good, very good. Excellent. Yeah, this is important. So this average is important. So you cannot really reason, I mean, okay, in continuous time you could reason actually about the endpoint, but in discrete time you definitely need to take the average just because of functions like this. So you know, my point is going to be the following. The function is not smooth, okay? So what that means is that the gradient can move from -1 to +1, you know, instantaneously. So if I do steps of size eta, I'm never at opt. Like I can, you know, keep going back and forth around this point. But you see that if I average, I get a much better value. So this averaging, in fact, is not, you're right. For the continuous time version, it's not necessary. In fact, you can see it here because the distance to opt is literally going to 0. But it's going to be very important for some of the other applications that I will talk about in the next 20 minutes. So this averaging matters. And we'll see next lecture that if you add smoothness, then you can take the last point. Yeah?
You said more curvature helps, right?
Yeah.
Well, like more curvature, then you make a bigger error if your eta's not needed?
Yeah, so, okay. So curvature helps really because if you start far away, then you know you will go very quickly. So what this means, you're right, that when you get closer, you can make bigger steps. But the point is, with strongly convex, instead of 1/√t, you can take 1/t. Because when you're far, you're going to make very big progress. So if you make it 1/t, then when you're close, you're only making a very tiny mistake. Yeah. I will probably talk about that also at some point. Okay, any other question? Okay, if not, let's just do the discrete time analysis. And in a sense, you know, the discrete time analysis is pretty trivial. So, yeah, like usually we just tell the discrete time analysis because it's so simple, but I find the continuous time one to be insightful also, even though it's more lines. Okay, so let's do this discrete time analysis. Okay, and let's even write a theorem. It's going to be slightly more general. So the theorem is like this. Let G1 up to GT be arbitrary vectors in Rn. So this is going to represent those arbitrary vectors. You can think of them as the gradient evaluated at the point on the trajectory. But in fact, it's more general. Then, and xt plus 1 is equal to xt minus eta gt. Okay, so you're doing gradient descent, but instead of stepping into a gradient direction, you're stepping into this gt direction. If you want, at this point, you can think gt is the gradient of the convex function, but it's more general. Then, what do we have? We have the following guarantee. If you take the sum for t equals 1 to capital T of the inner product of gt with xt minus x, then for any x in Rn, we have that the inner product, the sum of the inner product, is upper bounded by the norm of x0 minus, or maybe x1, x1 minus x Euclidean norm squared over 2 eta plus eta times the sum for t equals 1 to capital T of the norm of gt squared. Okay, and I want you now to recognize those two terms that we talked about, forgetting of initial conditions and variance term. Okay, so let's say corollary. If gt is equal to grad f of xt, and the norm of grad f of xt is smaller than L, then we have the following. Then what do we have? We have that the value of f at 1 over t, the sum for t equals 1 to capital T of x of t minus f of x star. This is smaller by convexity. It's smaller than the average of those things. And each of these terms, okay, maybe it's smaller than 1 over t, the sum for t equals 1 to capital T of f of xt minus f of x star. Each of these terms is smaller than 1 over t, the sum for t equals 1 to capital T of grad f of xt, inner product with xt minus x star, which by the theorem is smaller than, let's call it R1 squared over 2 eta t plus eta L squared. Okay, which is exactly what I wrote here. Right? It's exactly the same thing. Any question on the corollary? Okay, so this statement is more general than this one, just implies it directly. And we're going to prove this one, and we're going to see other applications of it. Yeah?
This sort of implies at the start of optimization, in order to calculate eta, you already have to know what L and T are.
Very good. Yeah, so yes. So in this class, I want to focus on the big ideas. So I'm assuming that you know those parameters. There are many, many ways to go around it, to go around not knowing those parameters. So for instance, capital T, it's not that important to know it. Instead of 1 over square root capital T, you can do 1 over square root little t. And that will work. Okay, so that's the first comment. Second one is this capital L, for instance, it can be replaced by a line search. So instead of knowing exactly, the value of the gradient, the norm of the gradient, it's enough to just search over the gradient direction. This R0, you need to know something about it, but often you're doing constrained optimization. I will talk about that in a minute. And when you do constrained optimization, R0 is just the radius of your set of constraint, which is something that you can calculate a priori. So all of those terms are different, R0, L, and T are different ways to, basically go around assuming that you know them. Yeah. Okay. So let's do the proof. So the proof, I'm just going to discretize the continuous time proof, which I erased, of course. So all we're looking at is this potential. Okay, we're looking at our distance to opt. So again, the picture, which I also erased, is like this. We have x star, we have x. We're gonna we would like to step in this direction, but we're stepping in that direction. Okay, and we want to know how much did we decrease the distance to opt. Okay, so let me write an inequality. So if this vector is A and this vector is B, okay, so you would like to go in the direction A, but you went in the direction B, how much does the potential decrease? So what was my potential? This distance was the norm of A squared. Now, my new potential is the norm of this gradient squared. What is this gradient? This gradient is A minus B, right? Because if I do B plus A minus B, I get to A. So minus A minus B squared. This is the decrease of my potential. And I can just expand the square. What do I get? the norm of A, they cancel, and I get 2 times the inner product of A and B minus the norm of B squared. Okay, so this is exactly the correlation progress. Okay, so again, it's telling me if A and B are correlated, then I make progress. Okay, this thing is decreasing. But I get a little error term, which is this variance term. Okay, so error term, or variance term if you want. Okay, which is the jittering around the gradient flow path. Now, look that we expect everything to be fine. B is going to be eta times something. So this is of order eta, and this is of order eta squared. So we expect that when eta is small enough, this term is not going to matter, and this is going to be the only one that matters. Okay? So we just use this identity over the quantities that matter, that we care about. So what are they? So x star minus xt, norm squared, minus the norm of x star minus xt plus 1 squared. Okay, xt plus 1 is xt minus eta grad f of xt. So this is equal. What do we get? We get twice. So what is A? A is x star minus xt. And what is B? B is minus eta grad f of xt. Sorry, and there is no grad f now. It's just gt. In a product with minus eta gt. Okay, that's our B vector. We're stepping in the minus gt, eta gt direction. Minus eta squared, norm of gt squared. Okay, I mean, that's it. Like, here we have the sum of the gt inner product with xt minus x star. Is going to be upper bounded by the sum of those guys. And we have the initial term. So let me rewrite. Okay, so let me just rewrite it. This is equivalent to eta gt, maybe even gt inner product with xt minus x star is equal to the drop. Okay, so x star minus xt norm squared minus x star minus xt plus 1 squared over 2 eta plus, I just normalize by eta, plus eta over 2, the sum for t equal, not the sum, just norm of gt squared. Okay, notice this is an equality. Like, there's no inequality. So when I sum over time, you know, this is a telescopic sum. I will just get the first term minus some term at the end, which I can just ignore. And here I get the sum of the norm of the squared. Okay, so this is the proof of gradient descent. So you see, it's really one line, which is why usually we don't go through this part. Okay. Good. So let's do some applications of this. Let me think. What do I want to do first? Okay. Before application, let me do another generalization. Optimization with constraints. So then what you can do is, instead of gradient descent, you can do what's called projected gradient descent. So PGD, projected gradient descent, is like this, xt plus 1. So I want to do a gradient step, xt minus eta, let's say grad f of xt. But this point might be outside of my constraints. I have some set k, This is my set K, and I want to optimize f subject to this constraint. So when I do the gradient step, maybe I step outside of this constraint. So if I do, the only thing I'm going to do is that I'm going to project back. So pk of this, where pk is just the Euclidean projection onto this set. And the easy lemma that you will prove in the program session, or maybe you did it yesterday actually, yeah, maybe, hopefully. So the lemma is that the lemma is like this: the norm of pk of x minus z is smaller than the norm of x minus z for any z in k. Okay, so when I project, I get closer to any point in the set, or to all points in the set. Okay, just get closer to everything. So if I know that my opt is somewhere in there, I only improve. It's only better to project. Yes?
Explain what you mean by the Euclidean projection.
Yes, yes, yes. Pk of x is just the argmin over y in k of the norm of x minus y. Okay, it's just the closest point in my convex set to the argument x. Yeah?
What if that's not unique?
Good. So this is, by convexity, it's unique.
Oh, yeah, sorry.
Yeah, no, but it's a good, yeah. Yeah, we're using convexity very, very heavily here. Yeah, this statement is absolutely not true. I mean, first of all, there is a uniqueness problem, but it's also just absolutely not true if you don't have convexity. Okay, this is really the convexity property. So, so in particular, a corollary of this lemma is that PGD, let's call this star, PGD satisfies star. Right? And the proof is just that it stems from the fact that in the analysis I'm looking at the distance. And the distance to opt is only improving when I project. So I just get even more decrease. So the decrease is even bigger. Yeah?
Just to be totally clear, you need f and k both to be convex here?
Yes. I need both f and k to be convex. And for this to be an algorithm that makes sense, I need k to be simple. So if you remember at the very beginning of the course, I said we're going to look at minimizing f subject to x is in k. And f was going to be something that we can calculate its gradient. And k has to be simple, and I didn't specify what simple means. Here you see one definition of simple. Okay, that you should be able to project onto this, this body. Okay, so if k was a combinatorial polytope, very hard to describe, then maybe it's hard to do. But if it's a Euclidean ball, it's pretty easy. Right? Projection on the Euclidean ball is just normalization. Yes?
So the way I see this, it's basically saying that we're converging towards the optimum, but then projecting. So
No.
So the objective that it's finding is the projection of the
No.
optimum.
No. So you have this convex function.
Okay.
Maybe it's defined over all of n space. And maybe the optimum is here.
Yes.
I'm not going to converge there. What's going to happen is that my gradient maybe here will tell me I want to go over here. So I'm going to do a little step, but then I'm going to project back. So what it's going to converge to is maybe this point. Imagine that I just have a linear function, which is going down in this direction. So this is my linear function. It's in this direction, theta. Okay, so my gradient is always pointing in that direction. So not exactly like this, but like that. Okay, so really if I were doing gradient descent, I would go over there. But what I'm doing is projected gradient descent. So I'm here, and I do this step. I end up here, and now I project back. Okay, so maybe in the way I describe it, it's going to converge to this point. I should have been more clear. Yeah. So I converge here, then I do a step. I project. I do. So I'm going to walk on the boundary, in fact. And when you say it like that, it seems very subtle and delicate, but it's not. It's just this. Okay. Yeah.
The minimizer within the constraint is not necessarily the minimizer's
No.
projection onto the constraint.
Exactly. Yeah. That's. Yes, they can be very, very different. All right. So let's talk about stochastic gradient descent, which is a workhorse of modern machine learning and also old machine learning, of all of machine learning, I guess. I don't know if Rob agrees, but okay, so randomized, or how do I want to call it? Randomized, stochastic, let's just call it stochastic. Stochastic gradient descent. So here is the theorem, or let's call it rather a corollary, again, of this theorem. So say that GT is a random variable. Oops, what's happening? Is a random variable. Yeah, maybe. Is a random variable such that the expectation of GT conditionally on XT is equal to grad f of XT. Okay, so I'm not going to step in the gradient direction. I'm going to step in the GT direction, which is just an unbiased estimator of the gradient direction. Not exactly the gradient, it's something which is just correct in expectation. And the expectation of the norm of GT squared, let's say, is bounded by B squared. Then, the expected value of f at the average point minus f of x star is upper bounded by exactly the same thing as before, r1 squared over 2 eta plus eta t b squared, which if I optimize over eta, this is, so opt over eta, this is upper bounded by r1b. Okay, and there are 2's everywhere, so over square root t. Right, there was a 2 also, a 1 half here. I mean, it doesn't matter, but it's just nicer. Okay, so what this is saying is actually very interesting. This is saying that if I do gradient descent, but I have noise in my gradients, I don't compute them exactly, you know. Maybe it's for efficiency reasons. I don't want to spend too much time to calculate it exactly. I calculate it up to some level of accuracy, and I hope that the noise in what's left is random. Then I will still converge to the optimal point at this rate. And here the averaging is very important. Right? The averaging is exactly averaging out some of this noise. Okay, is the statement clear? Yeah.
So I noticed in this, and then in the previous form of this, that final bound at the far end of the equation doesn't in any way depend on f of x. So like no matter what the curvature of my function is, that would still be true?
Yes. Yes. So yes, this is yes. This bound only depends on. So there is some dependency on f in B or in L. L is the norm of the gradients. And we're going to see if you make more assumptions and you want to improve, you want to have something better than this. Yeah.
This sort of seems, I'm just thinking, what if they have very large variances?
Right, so the variance is controlled here. I assume that the expected norm squared is bounded by b squared. Yes, you need something, yeah. Yes. So this goes back to a statement like this, a version of it goes back to Robbins and Monroe in 1951. I guess I don't give many references, but you can look it up everywhere, in my monograph or wherever. Yeah, of course.
About the variance. So should you be controlling the norm of GT or the direction of GT?
You only care about the norm of GT. The point is the direction is controlled here. Of course you care about the direction, but this statement is saying that the direction in expectation is a correct direction. And you have fluctuations around this correct direction, but you don't have like huge things that cancels out. This is a variance bound. That's the point. Okay, so let's see an application of this to an algorithm which is actually used all the time, which is SGD. Okay, so application, SGD, stochastic gradient descent. And we're going to see there are two different versions which are different. So let's say, okay, so SGD. So let f of x be the expectation of a certain loss function on this x for a pair a, y. Okay, and this is over a and y. Okay, so you've seen in statistical learning theory with Rob that we're making this IID assumption, so we're assuming that the world is giving us random features and random labels. Okay, and we have a certain distribution that we don't know. And what we really want to do is to find the best predictor in expectation. So that's what we care about. Now, how could we optimize this thing? We could try to run gradient descent. But if we run gradient descent, we have a problem because we cannot compute this expectation. We don't know the distribution. But in the statistical learning framework, what we have access to is an IID stream of examples. So using an IID example, we can compute an approximate gradient. Okay, so GT, which is equal to, let me see, the gradient with respect to x of L of xt at yt is a stochastic gradient. Okay, so I assume, so my assumption is assume a1, y1, etc., at, yt, etc., is an IID stream. Or an IID sequence. Okay, so I have this IID sequence. I can sample an image from my data set and have the corresponding label. So what I do is that instead of optimizing over the entire distribution, I just take one example and step in that gradient direction. Then this theorem directly applies. I have nothing to do. That's it. I mean, I just apply this theorem. So the expectation of this is correct. Okay, the expectation over at yt is correct. And I have a norm bound just assuming that each individual losses is controlled. Okay? Does that make sense? I don't want to say really more than that. Yeah?
I think some of us are not sure what A is, and also I'd like to know if A and Y are conditional on X.
Very good. So I have, very good. So, I mean, there are anything. How much do I? Rob, what notation did you use? X and Y, I guess? Yeah.
Instead of X, we have H.
Yeah, so in Rob's class, X is H. Maybe this is Rob. This is H, this is X, and this is Y. Okay, great. Yes. Sorry, so this is the difference between learning and optimization. So, you know, yeah. x is really what matters in optimization. So, I mean, what you're optimizing over, so you don't want to call it h. Anyway. Yeah, Renan?
You can't apply this anyway. You need some sort of bound on the loss function. If you use one of those hinge losses or something, then you get...
no, that's fine if you use the hinge loss. What's the problem?
Like, don't you care about the second moment and it can't just explode in some way?
I mean, the hinge loss, you see, it's...
For some other functions.
Okay. So no, I mean, yes, for some function it can explode. Of course, you need something, but the hinge loss, the logistic loss, all of those things are controlled. Yeah. You need L to be Lipschitz. This loss function. That's all you need. You know. I mean, if each one of those loss functions individually is Lipschitz, then you're good. You get this control. Yeah.
So we've shown that in expectation are f of the average as much as the truth, but can we bound the variance away from the truth?
Yeah, this is not completely trivial. So the answer is yes. But you might need, so for this type of bound, you can do it. It's not very hard to prove high probability statements. But as soon as you go into more refined inequalities with curvature or with smoothness, it becomes harder, and you have to play some tricks. But yeah, just like the answer to the question of knowing R0, L, and T, the same answer. Yes, you can do it, but it would take more than the 5 hours that I have to explain.
But there aren't any extra gotchas or...
No. If there was a gotcha anywhere, I tell you. Okay? So, yeah. Okay, so that makes sense? Yeah?
I'm confused about the definition of GT here. So this is the gradient at x, but the rest of this doesn't seem to involve.
Yeah. I mean, these are terrible notations. But what I mean is, look at this map from x to L of x, comma something. This is a map that depends on x. I differentiate with respect to that argument, and now I take the value at x equals xt. Yeah.
If the expectation also depends on x, do we still have the same?
Okay, yes, this was one of the questions. Here I'm assuming that I have this IID stream. That has nothing to do with my optimization procedure. It's given beforehand. This is my data set. Notice here, all I needed was conditional expectation to be correct. So conditionally on xt, it has to be correct. So gt could potentially depend on xt, and in fact it does here. But when I condition on it, this is independent of everything else. Like when I calculate this expectation, I can just ATYT is independent of xt. So when I calculate the expectation, it's equal to this expectation. Maybe I just write this inequality because it seems to be confusing you guys. The only thing that I'm using is the expectation. Okay, it's going to be so silly. So the expectation over ATYT of grad x L of xt ATYT, this is equal to the gradient with respect to x of the expectation over AY of L of xt AY. Okay, I did nothing here. Okay, I'm just renaming ATYT into AY and interchanging the derivative and the expectation. So what this is saying is that this GT is correct in expectation. It is indeed, this is the gradient with respect to x of f of x. And this is GT, the expectation of GT, conditionally on xt. Okay, so the expectation of GT conditionally on xt is indeed the gradient of f of x at xt. Okay. Now, let me say something important. So this is like one gotcha. Be careful. This is one pass SGD. Okay, I'm not allowed to revisit an example twice. Because if I revisit an example, then this identity is not true anymore. If I revisit an example, then ATYT is not a fresh sample independent of xt, because xt might depend on ATYT. So this analysis is only true. I have a huge data set. and I go through my sample once, and that's it. Okay, so it might seem silly, but the benefit, this is one pass SGD, the benefit, you directly control the generalization error. Okay, so right now, I believe Rob is spending some energy on trying to compute the generalization error using that you can control the training error. But here, this argument, which by the way was all done without working at all, directly controls the generalization error because you directly control your suboptimality gap on F, which is your test error. Okay, this is a test error. Okay, so you can only visit examples once, so that costs you something. You know, you're only going to get 1 over square root t, where t is your number, for example. You're limited, but the benefit that you get is that you control the generalization error. If you did multiple pass, what would happen? So we can analyze again with just the same corollary multiple pass SGD. It's just that you minimize something else. So multipass SGD is the following. So you have your data set of size m. So you have 1 over m, the sum for I equals 1 to m. So this is going to be your f of x. Of L of x on the pair ai yi. Okay, so you have m examples ai yi, and you care, this is your training error. Now, at each step, sample uniformly a data point. A data point which is just an index it in 1 through m. Okay, so you just sample, you just take one, you have this huge database of examples, you take one of them at random, and you calculate the gradient with respect to that. Okay, now you do xt plus 1 is equal to xt minus eta, gradient with respect to x of L of xt, ait, yit. Okay, so you can do that for capital T steps, and capital T might be much bigger than m. So you might do multiple pass. Then what does the theorem tell us? This is an unbiased estimator of the gradient of this f. So what you will converge to is to a minimizer of the training error. Okay, so that tells us that the training error goes down like 1 over square root capital T. Okay, and the benefit is that we can do multipass. Okay, so you see trade-offs here. One pass, you're very happy, you control the generalization error. Multiple pass, you can get to a better accuracy, but the price you pay for this better accuracy is that now you only control the training error, because your gradients now are unbiased estimator of the training error and not of the generalization error. Yeah.
Should the capital T be under the fraction?
Say again?
So that capital T should be in the denominator over there?
Capital T should be in the denominator, yes. Oh, over there. Yes. Yeah, thank you. Yes. This was a cumulative version. Yeah.
On the side, for the one-pass SGD, do you know of anything where ordering the data?
Good. Yeah, so, I mean, here order doesn't matter. This is like an exchangeable sequence. So, you know, I can apply any permutation, it's still IID. Right. But maybe what you wanted to say is multipass SGD, where you do multiple pass, but you don't take a random example each time. You go through them in order. Like that's one thing you can do. This is different, and this is harder to analyze. You know, experiments suggest that maybe it's better. Who knows?
I presume somebody's looked into it.
Yes, but it's not very conclusive. But yes, I can give you references. It's not a completely solved affair, this one. Yeah.
Thanks.
Yeah?
Is there an expectation on the empirical average over the L's? Or
Here?
Yeah.
Okay, very good. The key point is no. There is no expectation. So what I'm saying here is when you do multiple pass SGD, you're optimizing this guy, the training one, training error, not the generalization error. There are two different things. So what I said here is when you get a fresh sample every time, then this is an unbiased estimator of your test error. But when you revisit your example and you just take one at random from some fixed data set that you keep going over and over again, you get an unbiased estimator of the training error. So there is no expectation. All right, that's it for today.